everybody. Thank you for coming for the last technical session of this conference to dive with me into the world of coroutines, into Raft protocol. How many of you have heard about the Raft protocol? Oh. And about Paxos? A little bit less. So how many of you have tried to implement Raft by yourself? No? So it could be your next task to try to do it after my talk. Before we are going to the Raft protocol, I would like to introduce myself. I am the Vox Ukraine organizer, Java User Group Ukraine organizer Kotlin Night Conference in Kyiv, and also Kotlin Kyiv User Group co-leader. And as the DevOps Ukraine organizer, I would like to propose a little bit discount for 30% for our DevOps conference. After this talk, you also come to me and I will show the discount code again. So, what will be the agenda for today? We will start from the consensus algorithms, why we need it, and then as the one of its realization, we will stop to the replicated state machine. After we discuss the replicated state machine, we go to the Raft basics. Sorry for those who knows it. And after this, we will divide our Raft protocol into different building blocks to understand how can we implement it with Kotlin or other languages, and what coroutine primitives do we need to implement it. And after this, we will show some implementation. I will show you some implementation details. And after this, we will have a demo when we will see how leaders are elected, how log replication is going, and how new leader is re-elected after the old one is failure. So let's start. Why we need the consensus algorithm, and what is it, the consensus? Consensus help us to push the several machines or several servers work in coherent in the distributed space. What means work is coherent? It means that if you are doing something on one server, the same things should be done on another server. Why do we need it? Because all distributed systems are not reliable, and if one of the servers fails, another should become as new actors or as a new leader to prevent the fall down, to prevent the system fall down, or to continue to service the user request as quick as possible without the stops and without the delays. One of the most widespread algorithms for this is replicated state machines. We will discuss it a little bit later, and I will show how it's working and how they promote the states on different servers and nodes. The basic idea of this is that there is some leader, and this leader catch the client request and then replicate it to the different servers. If we have a response from these servers, actually, usually we should have the majority of responses. The leader apply this command by his transaction log, and then send the command to another followers, to another server, that they also can safely apply this command to their logs. And in this way, we can proceed it. One of the key points of this transaction log that if some of the node fail, another servers could continue to apply these commands on their own logs. Actually, and as usual, we need the majority of the system to be on the fly. If we have a less than majority of the servers in the fly, the system will stop. Why we need the majority? Because the majority is the good way to elect the leader and the good way in the point from availability, because all of these nodes will not crash simultaneously if you will not put them in the one rack. So it will help us to continue to serve our clients and provide reliable solutions. These systems play a key role in different distributed systems, such as HDFS, Hadoop file systems, the Keeper, which maintains a cluster in coherent state, and another one. One of the ways, as I have said, to implement this coherent algorithm is use replicated state machine. What is it about? We have the bunch of clients and we have the bunch of servers. What we will need? We will need that when we apply the command, for example, write number 6 to Z, it should be replicated on all of them. For this reason, we have and one more thing, when we apply this command, each command should be executed in the same order on all servers. So if we send the messages or if we send commands, it should be on the same order on all of them. And consensus algorithms help us to do this. How it works? It consists of some consensus model that ensures that log will be propagated correctly on all of the machines, and the number of available machines on the cluster will not less the majority. When it will be done and the leader receives the responses from the majority of the servers, it could apply it to its own log and execute this command. And in this way, if we have the majority, the system will not stop and will continue to work. And this system tolerates the different failure models. For example, if one of the servers will be not available, it's not very bad for the system will continue to operate. But we should tolerate not all failures, only the several part of the failures. For example, if the system will stop and go up, it will be okay. If the system crashed and then restarted, it also will be okay. But if the system will return us wrong answers, it will be not okay. This kind of problems is called Byzantine problem, and most of algorithms will not tolerate this kind of failures. And also, the messages could be delayed or could be lost. In this way, we should provide in our system as a solution to retry mechanism or detect that identical messages if we send them again. That's about the replicated state machine. How it works? The client sends the command comes to consensus model and is written to local log of the server. Then after it was written to the local log, it sends this command on another machines. And waiting while the leader will have the responses from the majority of the servers. When they receive the majority of the responses, it could apply it to its state machine, so it could execute this command on its own local machine and return the answer to the client. After the command was executed successfully, it also notified all another followers that they could also apply this command. So we have the system where all servers execute the same command in the same order, but with different it could be executed in some delay, not in parallel. So if we will ask, for example, in some point of time, this server, what state do you have? We can have the lost state. Not the actual state, it's the eventual consistency system. So we can get the stale state from this one of the followers. The actual state will be only on the leader all the time. And this system, when they receive the command from the leader about that it was applied, it also applied it locally. So why Raft protocol? Raft protocol implements this approach, but before Raft protocol, for more than 25 years, was another well-known protocol, Paxos. Paxos algorithm was designed by Leslie Lamport as the nice story about part-time Greece parliament in the Greece islands, how they can work together without sitting all in the voting room, but can implement some decision and agree in some decision. Paxos algorithm have the main problem that it is very hard to understand. It was described as the story, and previously it was not described as an algorithm. And another one problem with Paxos is that it is more harder to implement because it was described as a formal algorithm without thinking in mind about the details of its implementation. So when different companies have tried to implement it, they should do something stuff which not described in the basic articles and invent their own solution. And after this well-known and algorithm that was proved became a little bit another, and it's not the real algorithm which was developed and was proved by Leslie Lamport. And we have problems with it. So some guys from the Stanford have decided to implement the new algorithm to take in mind that it should be implemented in software and should be used as an enterprise solution for different products. So Raft implemented as a replicated log algorithm, as I have told before, and it was implemented by two guys from Stanford University. At the end of the talk, I will give you the paper where you can read it about. And it has a lot of adoption in the modern world of software. For example, Docker Swarm, Consul for service register and service health status in microservices world, Kudu, and RavenDB for distributed database system. So it has enough widespread. What is the part of the Raft consensus algorithm? The first part is the leader election. During the leader election, one of the server in cluster should become a leader and serve of requested from the clients. Another way that leader will appear if it crashes and or if the cluster will be partitioned or leader will be unavailable. Another nodes in the cluster should detect that there's no leader in the cluster anymore and should re-elect the leaders from them that will left in the another part of the cluster. When we have the leader, we can start to serve our clients in usual way, so we can execute the log replication algorithm as I have described it before. So it takes comments from the client, appends to its log, and then replicate these logs to another followers. And also, if the followers are unavailable, it should detect them if they become available again, and should replicate all the leaders log to the new one nodes that appear in the cluster. So how can we implement it? Before I will show this, I will show some demo from Raft website, where the authors provide a very nice explanation how it's works. So we have the bunch of servers. Now they are without the leader. I will start the countdown mechanism. When the servers will not receive some heartbeats from the leaders, they catch some timeout exception. And when the timeout will begin, they become the candidates for leader election and promote themselves as leaders for this term, for the servers. How they promote it? It send vote requests to all the followers, and if they received the majority of the votes, they can promote itself as a leader. If we have partition in the responses, vote responses, for example, like this, not like this, I should stop. So we can have the partition among the responses, so not the candidate have the majority of the voices. After this, if there is not majority, they should restart the re-election and increase the number of terms for which this node will promote it as a leader. And after several attempts, some of the nodes can reach the majority of votes. It will done due to using the random timeouts. Without this, it could be very possible to have the live log without this. So when we have the leader can serve the client request, for example. S3 now is access leader. So it serves the request. When it sends the request, it sends some command and copy it to its transaction log, and then replicate it to the majority, not on the majority, replicate on all of the nodes in the cluster. If you can see that S1 is not active, but the leader trying to ping it by sending the message. If I will resume this node, we can see that leader replicate its log to this node. Also, if the leader will stop, one of this node also can become a leader, related to the leader. And all the log will be the same on all of the machines. So now we actually, yes. I will stop it, and we will go to some details of the implementations. As you can see, there's several roles in the cluster that nodes can have. For example, all of them start as followers. The task of the followers to do nothing. They are passive and expect for regular heartbeats from the leader. If they not received the heartbeats during some period of time, they promote themselves as a new candidate to become the leader, and send to all members of the clusters vote requests. If they receive the majority of the votes, they promote himself as a leader and start to send in heartbeats through append entry messages. And also these messages will be combined with heartbeat messages. In the Raft protocol, they combine heartbeat messages and messages that replicate the log to another machine. So when the client arrives with some command, this command will be put in heartbeat message. Without the client's commands, heartbeat messages send it with empty body. So they combine heartbeating and promoting the replication log to all members of the cluster. During the election, if candidate discovers that there another leader, they become the follower, or if the leader understands that he is not new in the cluster and there is a leader with highest serving term, It's also degrade himself to the follower and became waiting for heartbeat requests. If you would like to implement the Raft protocol, you should implement only two methods. One of these methods is for serving vote requests to describe new leader, and another is append. Append request serving for heartbeat messages and accept messages with log replication. These two methods should work in parallel, and so should be worked in different threads, as we will see. What the Raft architecture we can propose for implementation? First of all, we have this process for vote request, for serve the vote request, and to serve the append requests. After this, we should start some procedure as we as a follower for waiting for heartbeat messages. The heartbeat messages will promote via append requests. Who will promote these messages? The leader will should promote these messages. So it generates heartbeats and generate replicated log messages through the append requests. And in this way, they inform the follower that there is an actual leader in the cluster. If a server becomes as a candidate, it asks for votes. Asks for votes using vote requests. How the candidate became the candidate? If there's no heartbeats from the server, it promoted as a candidate. Then, if everything is okay, it's promoted as a leader. And in any time, the candidate and the leader could become as followers as the previous. So, what building blocks we should have in our algorithm when we are trying to implement it? We should implement, first of all, the communication between client and servers, between different servers in our cluster. It's a very useful mechanism to use the remote procedure call, and we will use gRPC for this. gRPC with coroutines written on Kotlin. Also, as you can see, there are different states in our algorithm: follower, candidate, and leader. And we should move between these states depends upon what type of messages we receive and do we reach the timeout or not. Another way to implement the timeouts to restart the leader election, we should use reservable countdown timer for this. If we reach the timeout, we should run another logic, for example, to promote server as a candidate and then to become to the leader. If we receive the heartbeat message, we should resort the countdown timer and restart it again. Also, we should implement retry operations. Retry operations for voting and retry operation for trying to promote our log to another followers that are not active during the some period of time. And we should implement leader election, as I said before, and heartbeat messages. What type of code we can do for this? To implement communication between the nodes, we can use gRPC with Kotlin support. This library was written and available on GitHub. You'll see the link after, you can get the link after the presentation. Less than 2 hours before my session, I have added coroutine scope, as Roman Elizarov have told on his session, and now it's coroutine structure, coroutine ready for the code. Also removed some deprecated stuff after his talk. So the gRPC implemented use async messages to return, and also returns the default result. So it's fully coroutine supported. Then we should implement the state transition. How we could implement the state transition? It is very easy because we have another coroutine concept, channels. Channel is independent from different coroutines, and it was designed to pass some information, to pass some messages between coroutines. And when we will use it, we should pass this channel to different coroutines. And in one coroutine, we'll receive some message that we have pinged heartbeated as by the leader, that we are the follower. We will resort our heartbeat timer and restart it again. If there is no heartbeat messages, the heartbeat timer will escape, and we could start the candidate election. And for this reason, we should start the leader election logic. If during the leader election we receive some information, some message from leader that some leader has appeared, we should interrupt the leader election and become the follower. If we win the leader election, we move to the state of the leader and start append request and leader heartbeat messaging to our clients in the cluster, and propagate our log and to serve the clients with coming messages to our code. So this mechanism with channel is very useful for moving between states in coroutines. How we can implement resortable countdown timer? I think that it could be implemented in different way, but I have found this one. So what we will have? We have a timer, which is the part of the coroutine library, but it's the wrapper of the Java timer library. This timer is good for reasons that it could be cancelled, and after this we can create the new timer with the time after delay that should be executed some block of code. So when this timer is started, it's waiting some period of time, random delay, for example, and if nobody will call the resort method, after this timeout, they start the action in running block. It will be passed as a suspend function, and we will use it, countdown timer, in our followers logic to wait for append messages for the leader, and if no append messages has arrived, we will start some action for leader election, this one. So we transmit the state of the from the follower to the candidate through the channel and start the leader election precision. What another things we should have? We should have retry logic. Retry, which trying to execute some action, some block of code several times. When we need it? We need it during the election, if we send the vote messages to the server and server doesn't respond us. We send it again. We send it so many times as before we receive the majority of the votes or the election timeout will pass. We will see how to implement the election mechanism a little bit later. We use this empty cache exception. Why? Because we are trying to do this logic in many cases because we could not reach another server, and we have some different kind of exception. It's not I/O exception, it's exception wrapped by gRPC stuff and so on. So we are not correctly cache them, but you can put some, for example, logging mechanism to show how many servers active in your cluster. If you would like, you can also add some delay between retries to not spam our network very fast. So it's very simple logic to implement time mechanism. Now it's one of the most complicated part of this algorithm is leader election. To elect the leader in the cluster with 5 nodes, we should only need 3 responses. After we will receive the 3 responses, we could cancel all other requests, retry requests to other servers, and promote ourselves as a leader. Also, if we received if all these nodes will not vote for us, we also should stop the voting and become the follower or restart the leader election procedure. For this reason, I have used countdown time latch to count how many responses I have got. I think that using channels and the example of code that Roman Elizarov has shown us a couple hours ago, we could implement it in a different way, but countdown latch is not the Kotlin and Coroutine way, but it's okay for now. So what we are waiting for? We are waiting for the majority of votes we will receive by our followers. So how we can do this? For each server, we retry to send some vote requests. If we received this vote response, then doesn't matter this was given for us or not, we will decrement our countdown latch. After all of these countdown latches will be equal to the majority, we can proceed by the following code. Another restriction for election mechanism is that we have election timeout. So there are 2 reasons when we can proceed to the following code after countdown latch. If we have received the majority of votes, responses, or the election timeout will pass. And then we can do another logic. As you can understand, we should send vote requests, not sequentially. We should do this in parallel. For this, we are using coroutines. This is the old stuff, how we have used the coroutines before the new one. So we created the job, pass this job to the launch coroutine. When the countdown latch will trigger, we cancel and join all these retry jobs. With new coroutines, the code became a little bit simpler. So we create the coroutine scope, and inside this scope, we also use launch coroutine. And when the countdown latch is triggered, now we can only call cancel children, because all of these coroutines are working inside coroutine scope and will interrupt it after we can call cancel children request. To implement heartbeat as a leader, to send the append request to our nodes and to propagate our log to these nodes, we are using fixed rate timer. It's the wrapper of a Java timer, which also implemented in Kotlin. And for them, we are using also for each and launch append message in a coroutine. If we have the exception, IO exception, server is unreachable, we are using retry mechanism in the next round of timer rates. So, for example, this period of time, 2,000 milliseconds. So, how it works? I will show you the example. I will start 3 servers, and we will see what we will have and how the election time will pass. So we are using Ktor as a web server to serve the client request. After our server started, it started as a follower. With zero term, term is a linearizable solution to detect which message is more actual than another, or which leader is more actual than the previous one. So now, as we haven't received information, heartbeat messages from the leader, this follower, this server one, nominate himself as a candidate and start the election. He couldn't win the election because he's only one in a cluster. So to win the election, we should have at least 2 servers acting. Now we can see that election timeout, that this round of election was timeouted and the new election was started. It's the demand of the Raft protocol algorithm to found the still nodes. Now what we are doing, we can start another server. When after this server is started, it will receive vote request from the first one. So as we can see, it received the vote request and the log has changed. Visually, we could see it. So we have received 2 votes. It's the majority for 3 nodes, and after it, we have the leader. Leader is server 1. After this, after it became the leader, it have started call append and heartbeat messages to all members of the cluster. So it's pinging the first one, second one, and the third one server. For the third server, we have exception because we have not started it. We have started it a little bit later. So what we can do now? We can start serving client request via Ktor web server. And where is my server? So without any commands, the state of the server log of the leader is empty. I will use not very correct approach to send the message to the server through GET request, but it's okay for the demo. Don't do this in production. So what we will do? We will send some command add. And we will see that the server 1 log has this command. What about server 2? The server 2 also has this command. If we will send 1 more command to our leader. 1, 2, 3. We can see that the server 2 log also have these comments. Now we will start server 3. We can check that it is not actually working. So we will start it. After the server will start it, the leader which sent this server the regular append messages and heartbeats will detect that the server is started and will replicate his log, server log, to this new server that has appeared. If we have asked information about the server, its log is empty because it's eventual consistency approach, but when we will check it a little bit of time also, yeah. They detect the leader heartbeats one, and now if you can see, this something number is increased. 1, 2, 3, 4. This shows that the messages from the leader is propagated to the follower server. And after this, and we can check that their logs are identical. What we will do the next, we can switch off our leader to see how the election new leader will be started. So we have, for this moment, 2 servers. Server 2 and server 3. After the timeout, both of them will send vote requests to another servers, and some of them will be the winner. So now we can see that server 2 became the leader. Server 2 became the leader. Now, after this, server 2 can serve client requests, and when we submit some command to them, for example, cmd subcommand, it will appear here. Also, you could see that there is a number, this is the term number, and if the number is changed, it means that the leader was changed. And the same information we can see on the leader 3. The server 1 is not active, but if we restart it, we can see after this that it also will have the same log. The log will be propagated to him. If the server is not crashed and will be separated from other servers, it will be also OK, even if it was the leader. It will detect that the new leader appears in a cluster and downgrade itself from the leader to the follower. So timer resorted, and we can see that we should have the empty log for the beginning, and after several iterations, come on, yeah. Not now. After several iterations, yeah, timer resorted and heartbeat message was received. It's null messages, but we can see how the leader propagate his messages to the new nodes that appear in the cluster. So it is the basic implementation of Raft protocol. So return to my presentation. And also for this, I have used very simple Ktor Framework. Before using Ktor Framework, I have used Javelin, another lightweight web framework, web server. But in comparing with Ktor, Ktor is much faster. So you can detect it during the startup time of your server. So we have routing, forget. So also you can put this post request and call and respond messages for requests. So thank you for coming and have a good evening.